Welcome back. We're now in chapter 2 of Kuchemann, and the first thing he ends up deriving is some of the equations of motions that led us to start to try and estimate things. Again, the power of this was, kind of pre-CFD, pre a lot of these different things, so that the framework you have to first develop. And he does a good job of kind of walking through where we might start off at like Boltzmann's equations, right? And he doesn't derive, it just kind of walks you through in words, like what assumptions we're making. It's collisional and viscosity. And you can get to, gas dynamics. And then, from there, it's nice to walk through the assumptions because at some of these speeds, we actually will start breaking some of these things. It's not, you don't just start with Navier-Stokes, right? And so you can get to gas dynamics. And then from there, you can get down to Navier-Stokes where you have, sort of continuity is now established, viscosity is now established. I remember even like in gas dynamics, like in a rocket engine, like there are times where we absolutely do not have equilibrium, like in a nozzle, for instance. So there's some really cool things. In fact, like all the original chemical lasers were because of rocket engines and weird reactions where you freeze things and they laze out. Like it's pretty cool stuff, okay? But you can get to Navier-Stokes, and that's sort of where we're starting. And this concludes compressibility, right? And then, thinking through, boundaries and wakes and Lagrangian Lorentzian formation. So to start off with, we're going to talk about an inviscid flow. So even though we can get to here, we're going to kind of pause and say, all right, inviscid. And so what we mean by this is viscosity is 0. And so if you take a look at the Navier-Stokes equation, I'm not going to write them down. I'm going to end up using a lot of the board. That the viscosity term drops away. And then if you have irrotational, which means no vorticity, and I'm going to start using the standard compact Einstein framework. Okay, but just writing it down here explicitly, irrotational would mean the curl of the velocity field is equal to 0. Now, in the Einstein formulation, kind of write down here a couple different things. So the gradient of a scalar, you would write as del by del x of I of phi. And I'm going to further compact it, which you will see a lot in fluid mechanics because we end up carrying these quite a lot. I'm just going to say del of I to represent sort of a spatial derivative here, okay? Laplacian, so if you had a sum, say Laplacian, this is just del I phi. And so this actually, every time you see the two i's or two j's or whatever it has to be, it's actually an implied sum. So here there's a sum over I from 1 to 3. Okay, and so then a curl is epsilon I j k del j v k. And then epsilon I j k, if you haven't seen that notation before, sort of just walks through. For 1, 2, 3, it's defined as 1. For 3, 2, 1, it's defined as -1, and then all the combinations therefore. And if one of the terms is equal, it's 0. So this is going to be helpful notation. It might be new to you. You can go look in the book. He doesn't use this notation. He uses kind of a standard notation, but that's why it gets really, really lengthy. Okay, even this is going to be super helpful for us. So if we have these assumptions, okay, I kind of wrote down Inviscid, but let's write down our continuity equation, and then I'm going to come back up here and do a lot of the work. So just remember continuity, conservation of mass. We'd start off and say d of rho u dt is equal to 0. Okay, and so that's del j of rho uj is equal to 0. And I know I drew a line there, but come down here and I'll finish it out. Okay, and so I'm just going to chain rule this. And so the final part then is of I have a ui del I of rho, it's an I, plus rho del I ui is equal to 0. Okay, so that's continuity collision. That's going to come back here in a second. So then going to the momentum equation, and I'll write this rho uj del j ui, and steady, by the way. I'm writing the time term here. and that's equal to negative del IP. Okay. This is kind of the first step here, is that we're going to take a look at this pressure term and say, well, what if we said this is really, we'll take the derivative of pressure with respect to density, and then I'll take the del I of the density. Okay. So kind of a chain rule. And then in particular, though, the trick that they usually then say is this is an isentropic relation. So if I follow this from an isentropic relation, this is just a number if it's isentropic, and we will go ahead and define that number as c squared. And no surprise, it's actually going to end up being the speed of sound. Okay. So from that framework, okay, then we can actually come back and say, so one more time, uj del j ui is equal to negative c squared over rho, and then del I of rho. Okay, well, let's come over here to the density equation, and we're starting to see a form that looks kind of okay. And so this is a momentum equation, and it's a vector. So just look at this term again. So this is, if I was to write out this term, it's a sum over j from 1 to 3. And so I'm going to use the standard notation where my velocity field is u, v, w. And so this term, if I was going to look at the x momentum just for a second, so this would be, I'm looking at u, then it would be u du dx plus v du dy plus w du dz. Right? That's this one term written out. The j's get summed, so it's the x velocity j times the x derivative of u, and but the I, this is basically this is I equals 1. Okay, and so this is a vector, and so I'm actually going to go back and write, and I'll just finish this out since it's here, minus c squared over rho, and then this would be the x derivative of rho. Okay, so I'm going to multiply this momentum equation. I'm going to come up here, use a different color, and take this whole thing, and I'm going to multiply it by u of I. Really, I'm taking the dot product of this with the x momentum, the y momentum, and the z momentum. Okay, and so now we have a ui uj del j ui, and that's equal to a negative c squared over rho ui del I rho. Okay, well, let's look at this. If I divided by rho, then this whole term is actually then just c squared, and then it's looking for del I rho, so dividing by rho, c squared, and then I have del I uj. Okay, and so that is, it's kind of messy, but that's one form of the equation right now, and this is one scalar equation. And then the final step that we get to do is actually coming back here to this irrotational thing, and we're going to use a property that if I have a scalar, so if I said that my velocity vector was actually just the gradient of a scalar, then irrotational, if I'm trying to take the curl of the gradient of a scalar, that is actually, you can work out the math, it is 100% zero. There's no way a scalar does anything other than turning this into zero. So we can then use this form, okay? And we can come back in here, and this gets beyond messy, but following out for just a little bit longer, this becomes, so ui is del I phi, uj is del j phi, and then del j ui, that's del j del I phi, so it's a second derivative, okay? And then that's equal to, I'm actually going to go ahead and divide by c squared on this term here, and you'll see why in a second. That's equal to del I del I of phi. Okay, so these are velocities. Remember, this actually was ui and uj. And so if the speed of sound is way bigger than ui uj, this entire left-hand side goes to 0, and we actually get back our incompressible, which is just, this is just the Laplacian, right? It's just the Laplacian of the potential. So we would get incompressible. Well, we can actually hold this equation a little bit longer and still get some compressibility out of it. And that's the power behind kind of this first step of Kuchemann in chapter 2. Okay, and so yes, we can come back, and like Kuchemann's saying, we can come back and we can solve this numerically. Okay, we can make simplifications, we can make linearizations and solve it, and that's where a lot of the power is going to come in. Okay, and so what I'll then kind of try to do here for the last little bit is say, I'll draw it top right. Imagine we have some sort of airfoil, and then there's a velocity coming at it, and then there's an angle on this airfoil. And we're actually going to define the coordinates such that this is x and this is z. So I'm going to get rid of the y velocity. Just sticking to Kuchemann, I would have actually kept that is x and y. And so if you do that, then when you end up working this out, okay, let's come back to here. So the c squared, so end up defining u, right? The u is going to be a large velocity plus a fluctuating velocity, and it's actually this is cosine of alpha, okay? And then w will be this sine alpha and fluctuating velocity. Okay, so if you worked all of this out, you'll end up having a form which is del u prime del x, and I'm actually going to write it out. Okay, 1 minus, and then this is the full u over the speed of sound squared. Okay, and then there's minus not del but 2, and this is the fluctuating, or not fluctuating, the small component with respect to z, and then u w full over c squared, and then plus the derivative of the small component with respect to z, and then 1 minus, and then the full w velocity with respect to c squared. Okay, that whole thing is equal to 0. Right? So that again, that happened by taking this equation in its compact form, writing it all the way out. The y variables go away. The x and z have sort of a major component and a smaller component. I got tripped up calling it fluctuating from my turbulence days. Okay, but then you can take a look at this, and you can say, you know what? This is mainly, the flow is mainly along the x direction, so I can pretty much just call that the Mach number squared. Okay. This term is going to be small, right? What's the gradient of the small velocity in the z direction? Small. Okay. And then the change in the z direction with respect to the speed of sound, this thing is going to be small. Right? And so then in the end, you can end up writing this whole equation really compact. Namely, this whole thing becomes du prime dx, and then this picks up a beta, because we're going to define, so beta squared. We're actually defining beta is the 1 minus Mach squared to the 1/2, and then plus d w prime dz equals 0. So we'll come back next time, because I've now filled this board with equations, but this we can go through and solve, where you take a look at the boundary conditions on the surface of the airfoil, and this is good enough for that kind of approximation, and it does include some compressibility in there, right? As long as these terms were true, and then we'll talk a little bit about the condition that you end up having to do here on the end, called the cut condition. So this is just the framework how how Kuchemann's going to start and get to these equations that we can then kind of linearize, solve, and start to get some understanding that includes some compressibility. It's not just fully incompressible. Okay, we'll see you next time.